Good afternoon, everybody. Welcome and thank you for joining us for the 2020 and 2021 medal talks for the Canadian Association of Physicists. My name's Rob Thompson. I'm past president of the association, and I'm at the University of Calgary. I would like to take a moment right now to acknowledge that I am speaking to you from the traditional territories of the people of the Treaty 7 region in southern Alberta, which includes the Blackfoot Confederacy, comprising the Siksika, Piikani, and Kainai First Nations, as well as the Tsuut'ina First Nation and the Stoney Nakoda, including the Chiniki, Bearspaw, and Wesley First Nations. The city of Calgary is also home to Métis Nation of Alberta, Region 3. Opening us up today is Dr. Alexandre Blais. Alexandre was the recipient of the 2020 CAP DCMMP Brockhouse Medal for his pioneering contributions to and continued leadership in the field of quantum information science. His theoretical research has greatly influenced the forefront experimentation in this field. And so without any further ado, I am going to release the screen and invite Alexandre to share his screen and proceed with his talk.
Okay, thank you. Thank you for the introduction. Hi, everyone. So indeed, I will be talking today about quantum information processing with superconducting circuits. But before going there, of course, first of all, let me acknowledge and thank the Canadian Association of Physicists for this recognition. But also my colleagues at the Institut Quantique and at the University de Sherbrooke more generally. So this award really is the recognition of the work of a large team of current and past members over the last 15 years where I've been at the University of Sherbrooke. So this wouldn't be, of course, any of this wouldn't be possible without this amazing team of people. So if you follow the news, any scientific news, technical news, but also just casually read the New York Times or the Globe and Mail, you will nowadays often hear about quantum computing, and you will see things like claims of quantum supremacy by Google using superconducting quantum circuits, something which dates already back from to 2019. Since then, other groups have claimed similar achievements. You will also see more recently IBM introducing with great fanfare their 127 qubit device. And with that comes headlines of the sort that quantum chips will outperform standard chips in 2 years, and that these are game-changing. So my goal in this talk is to tell you about a little bit of the history of the field, but also cut through a little bit of this hype and tell you where the field stands now, but also what are the challenges that are upcoming. So first, let me start with a little bit of an evolution of superconducting quantum processor over the last few years. And through that, let me tell you a little bit about my story, where I played some role along this line. So the idea of using superconducting quantum circuits to realize qubits, to realize quantum information processors, really dates back to the late 1990s, where the first experiment realizing a superconducting qubit was performed by Yasu Nakamura, who was then at NEC in Japan. And that, in fact, coincides where I started my master's degree in the field. And when I said to one of my professors that I wanted to do a master's degree in quantum computing, the reaction that I got at the time is, well, okay, you do something fun for your master's degree, but okay, please do something more serious for your PhD. Well, the good news, I guess, is that I'm still working in an area which I consider fun, so that's great. Then I moved on after my graduate studies at the University of Sherbrooke in superconducting quantum circuits. I moved to Yale, where we introduced what is known as the circuit quantum electrodynamics architecture. And that was an architecture that embodied all of the essential, the necessary requirements for a system to be a quantum computer. Of course, there were many, many challenges ahead, but at least for the first time, there was in superconducting quantum circuits a path, a way to maybe one day push these ideas and realize these ideas. And so the first experiment, the first theoretical proposal and the first experiments were in 2004. But these experiments and theoretical proposals were very much based on the very first superconducting qubits. And their properties were by far not good enough to imagine one day scale this up to hundreds, to tens, hundreds, and certainly not thousands of qubits. So we really needed new qubits, simpler qubits, but also qubits that simply worked, that had much better coherence times. And this is when, again, working with a group at Yale, we introduced the trans-bond qubit, which is now used essentially by all companies and groups working on superconducting quantum circuits. And so then bringing these ideas together, it was possible to realize the first quantum algorithm on superconducting devices in 2009. Of course, since then, the field has moved quite far, again, with these 127 qubits and the quantum supremacy. But in this talk, what I would rather do, rather than talk about talk about these large quantum systems, is rather open the box and tell you how do these systems actually work, so that when you hear these announcements, you can understand a little bit better. Okay, this is what it actually means. There are in fact challenges still ahead. So before thinking about superconducting hardware specifically, it's good to take a step back and ask, okay, when we're thinking about a physical system that is supposed to embody a quantum computer, that is supposed to be used as a quantum computer, what are the essential requirements that we need? And these essential requirements were first introduced by David DiVincenzo already more than 20 years ago, but they are now called the DiVincenzo's criteria. Essentially, what we need, of course, are qubits, lots of qubits. These qubits should be two-level systems that are well isolated from anything else, such that their energy levels are sharp. In other words, their lifetime is very long. Their energy relaxation time, but also their phase coherence times are very long. Of course, we need to control these qubits to do meaningful calculations. In particular, we need single qubit gates, the equivalent of a NOT gate in classical computing. But we also need the equivalent of a NAND gate in classical computing. We need 2 qubit gates. And these 2 qubit gates provide the important resource that we think quantum computers use to achieve speed up, and that is entanglement. So without these 2 qubit gates, there is no entanglement. So you need ways to controllably make qubits interact. And at the end of the day, of course, you need to read out these qubits. Otherwise, well, there's no point in doing a computation. So just by listing these desideratas, we already understand that well, that has to be difficult. In fact, because these requirements are in a way conflicting. On the one hand, we really want isolated quantum systems that have very long coherence times. And for that, we want to isolate them from anything else. For example, if we could encode information in a neutrino, right, that would be ideal, because any superposition will not be decoherent, will not be perturbed by anything else. The neutrino can go through planet Earth without any change. But of course, a neutrino would be a terrible qubit because there's no way to access it. There's no way to control it. There's no way to measure it. There's certainly no way to entangle these neutrino qubits. So we want isolated qubits because coherence times have to be very long. But at the same time, we want these qubits to be strongly coupled to the external world to be able to control them. And so satisfying these somewhat contradictory requirements is what makes building a quantum computer difficult, but it's also why it makes this a fun research area. Lots of challenges, lots of things to think about, lots of things to solve. Okay, how do we realize these ideas specifically with superconducting quantum circuits? Well, here we will use what we'll call transmon qubits. And as I'll explain in a minute below, these transmon qubits are essentially two-level systems whose transition frequencies between 0 and 1 is in the microwave frequency regime, a few gigahertz typically. Okay, and as I'll also introduce a little bit later, we'll be able to control these qubits individually simply by pulsing voltage on them, okay, shining microwaves essentially on these qubits in the same way that we would shine a laser on an atom to control transition between, say, S and P orbitals. Excellent. So we have our qubits. There's are called transmon qubits. I'll come back to them. I'll show these transmon qubits to you in a minute. To satisfy the other requirements, what we do is we embed these qubits in a microwave cavity, which I represent here by these two mirrors that are facing each other. And this microwave cavity plays two essential roles. The first role is that if you shine microwaves at the input part of the cavity, the microwaves that are transmitted, in fact, carry information about the qubits that are in the cavity. And in this way, by shining microwaves and measuring the output field, you can measure the 0 and 1 state of the qubit. This is how you read out your qubits after computation. Excellent. So that's the first role of this microwave cavity. The second role of the microwave cavity is to act as a quantum bus, a way to mediate interaction between the qubits. For example, say you've prepared some interesting state of the leftmost qubit. What you can do is apply a pulse on that qubit to transfer that interesting state, that excitation, as an excitation of the microwave cavity. And that's called a microwave photon. Essentially, you transfer the excitation, which is in the transmon, to an excitation of the cavity to a microwave photon. And then you can pulse back this excitation to any other qubit which is living in the same cavity. And this way you can entangle, you can mediate interaction between any qubits, even if they are not nearest neighbors. This is why I'm saying that this is acting as a bus, as a quantum bus. Okay, so what we have again is transmon qubits. We can operate them by shining voltages on each of them. We can measure them by embedding them in a cavity. And the cavity also plays the role of mediating interaction. And so generally, this is known as circuit quantum electrodynamics. That's the analogy of cavity quantum, cavity QED now realized in circuits. I will show you actual sample pictures in a minute. And what you will see are not mirrors facing each other. The cavities are realized in practice in different ways. In fact, there are many different ways to realize these microwave cavities. And the way, one way which is quite standard, is simply to realize them as a small superconducting wire whose length corresponds to the wavelength that we're interested in. Here again, microwave photons. So typically, these wires will be something like a centimeter long, and we can connect multiple qubits, which, as you will see in a minute, are a few hundred microns big. We can connect a few of these qubits to the same cavity. Okay, so this is circuit quantum electrodynamics with transmons. How does it look like in practice? What I'm showing here on the left is a sample which was given to me by my friend Andreas Wallraff at the ETH Zurich. So this is probably something like 5 years old. So by now this is really a dinosaur, but I think it illustrates clearly the key features of these processors. And these key features remain the same now, even if you have 100+ qubits. So if we were all in person, what I usually do is I bring this with me, and I would each of you could hold it and essentially look at the qubit yourself. And so what you would see if you were actually looking at this chip, so first you see a PCB board where there's connectors. We'll come back to these connectors below. This is where you'll shine microwave voltages. These are your input-output ports. But in the middle of this chip is where the real action happens. This is where you have the superconducting chip. In fact, this chip is sapphire, or any good dielectric on which you've evaporated aluminum. And if you take an optical image of that chip, you will see in one of the corners an object which looks like this. And that object is a transmon qubit. Dark is the substrate. All the beige are the ground planes. And the transmon qubits is really this white object. And what is this? Well, all of these, this is a false color image, of course, and everything which is white or beige is a thin film of aluminum. And so what you're seeing essentially is that a transmon qubit first is a big object. You can literally see it with your naked eyes, and is two metal islands, two aluminum islands that are facing each other. Well, that's simply a capacitor. And that these two islands are linked by a small wire, which has an inductance. And what you have is essentially an LC circuit. That's simple as that. The transmon qubit is not quite, but almost an harmonic oscillator. So a capacitor and an L. And we know, of course, that quantum mechanically speaking, you have discrete energy levels. Excellent. So there you go. You have something which looks quantum mechanical. The problem here is that harmonic oscillators are always in the correspondence limit. They always behave classically. And as a result, if you can prepare the ground state of these systems, which is easy to do because the transition frequencies in the microwaves is much, much smaller than the temperature at which these qubits are operated in dilution fridge refrigerators. So it's easy to prepare the ground states of these systems. But then if you want to pulse the system with a microwave tone, what will happen is that the system will simply go to a coherent state. There's nothing which will restrict the evolution of the system to the first two states. The system will leak out and explore all of the large Hilbert space of the LC oscillator. And that's not what we want for a qubit. A qubit should be restricted to the first two levels, 0 and 1. And so the trick is, again, to use superconductivity. So what we do, in fact, is that if you look at this skinny line, it's interrupted here by a Josephson junction, an SIS, superconducting insulator superconducting junction, which essentially plays the role of a nonlinear inductor. So we replace this linear inductor now by a nonlinear inductor. The potential well of a nonlinear inductor has a different shape than that of a harmonic well, an harmonic oscillator well. As a result, the energy levels have to readjust to that. And what you notice is that the second level has lowered a little bit. That means that the transition frequency values 0 and 1 and 1 and 2 are no longer the same. As a result, you can really address only these first two levels. If you prepare the system in its ground state, I've just said that's easy, and connect a voltage, a microwave source to the right port here. So this microwave source connects to the coax to the connector here. That connector, there's a little transmission line that brings the power to the qubit. So that source ends essentially here on this brown little wire that I hope that you're seeing. This is where this circuit terminates. At that point, you apply a voltage, and that simply drives the transmon. And this way, you can do, for example, a bit rotation. By applying the right voltage, you can go from 0 to 1. Great. You can even this way prepare superpositions of 0 plus 1. Of course, in a quantum computer, you want to be able to change both amplitude and phase. And so the way to do that is to use another port, this port now, and also to change this Josephson junction by a squid, by a pair of junctions. And if you apply a flux through this wire, through the squid, what it does is it changes the effective frequency of this oscillator. And as a result, you're able to control the phase of any superposition. Okay, so bit rotations, phase rotations, different parts have different results. At the end of the day, you want to read out, as I said. And you do this by applying again a tone at a different port. say, this point here. And so this microwave voltage will now travel through this line that you're seeing here. And that line is exactly a segment of the resonator that I've presented before. Remember the wiggly line? Well, this is just a small segment of that resonator state, of that resonator. So when I was saying we place a transmon in a cavity, this is what I meant. We place a transmon nearby to the center conductor of a transmission line resonator. Okay, and so by measuring the transmitted power, excellent, you can read out the state of the qubit. Finally, if you look again at this chip, what you would see is that there is not one transmon, but there is in fact 4 transmons on this chip. You would see a second transmon, which looks exactly the same. And you would see that they are connected by more wiggly lines, by more transmission line resonators, by more of these cavities. And by again applying pulses, microwave pulses at the right ports, you can activate the 2 qubit gates that I talked about. So excellent. We have all of the ingredients that we needed to prepare any states that you could be interested in, both single qubit gates and 2 qubit gates. And these general principles are really how the processors by Google or IBM are working. One thing which I find really fascinating here is that, as I said, you can look at these. If we were all together, you could actually see the chip. You could actually see on the chip where the qubits are. You could see the qubits with your naked eyes. And moreover, you would see that these qubits are separated by something like a centimeter, the size of this transmission line resonator. And so what I'm saying here, what I'm claiming is that you can entangle 2 macroscopic objects, hundreds of microns, large enough for you to see, that are separated by macroscopic distances, a centimeter. So this is really not our usual definition of quantum mechanics, which is, according to some dictionaries, the physics of subatomic particles. No. Quantum mechanics is just the physics of the right conditions. And here, using low temperatures, superconductivity, and the right microwave engineering, we're really able to access these right conditions in macroscopic systems. And these ideas this idea of entangling 2 qubits can be pushed to much larger distances. In fact, there's nothing which limits you to something like a centimeter. You can simply build a longer and longer transmission line resonator, and in this way, entangle remote qubits. In fact, the loss per meter of a superconducting transmission line is pretty much on par of an optical fiber. And so in principle, it's possible to send microwave photons at a long distance. Of course, the problem is that these transmission lines have to be cold, very cold, for this to behave quantum mechanically. So that's not as practical, of course, as sending an optical photon. Nevertheless, you can push these ideas. And so this is a picture of an experiment that was done at the ETH Zurich in collaboration with my group at the Institut Quantique, where there are now not one dilation refrigerator with 1 qubit, but 2 dilation refrigerators that are connected by a transmission line, which has been refrigerated, which has been cooled down to cryogenic temperatures. This is why it's encased in this metal. And in this way, it was possible to entangle 2 qubits that are separated by 5 meters. Okay, it was possible to prepare entangled state of these 2 transmons in 2 dilation refrigerators separated by 5 meters. And now the group in Zurich can do this with fridges that are separated by 30 meters. So there's some interesting physics to explore here. Okay, so coming back to quantum computing, this is really how these ideas, for example, quantum supremacy, were realized with transmon qubits, which are represented by crosses here, and mechanisms to couple them, illustrated in blue here. The same is true for this 127 chip by IBM. And now if you find a better resolution image than what you can probably see on your screen, and you squint, you will be able to start seeing the different ingredients that I talked about. The cool thing on this chip is that there are a number of separate chips, of separate silicon slabs. And on one slab, they have built transmon qubits, 127, with their coupling. On another slab, another substrate, they have the readout resonators. So you see all of the wiggly lines everywhere. And finally, on a third slab, there are the input outputs to the resonators. This is how you address, for example, a qubit or a resonator, which is at the center of the chip. Okay, so these ideas can be pushed. Okay, excellent. One thing which is crucial to say is that despite all of these successes, there is much to be done, right? Building a quantum computer is in no way just scaling the ideas that I just described. New ideas will be needed. And in particular, new ideas are needed in one area, which is known as quantum error correction. It happens that quantum information is much more fragile than classical information, is more subject to errors. And if you encode your information in a single qubit and there's an error, it's lost, it's over, it's gone. And so we know in classical information that redundancy can be exploited to protect information. For example, if I encode one logical bit in 3 physical bits, or one logical qubit in 3 physical qubits, and there's an error in one, I can recover, in principle, this information. The question is how many qubits you need to robustly encode one, how many physical qubits you need to robustly encode one logical qubit. And the answer seems to be, at the moment, a lot, a whole lot. You will probably hear from Robert Rosendorf later today about these ideas. Robert has really pioneered some of these ideas. And what we know, following Robert's ideas, is that protecting a single qubit from errors may require up to thousands of physical qubits. And so if you want to do a task such as factoring a 600-bit number, which requires something like 1,000 logical qubits, you may need between 1 million and 1 billion physical qubits. That's really daunting. And so really we need to improve everything here. We need to improve the qubits, the gates, the readout, but also we need to improve the codes that require much less physical qubit per logical qubits. And there's interesting breakthroughs that have happened in that direction in the last few years. Let me mention one experiment which was very recently, which was submitted, which we posted on the archive as recently as I think December, well, early December, which is the first realization of these ideas, the so-called surface code, where we encode a logical qubit in a 2D grid of physical qubits. So this is an experiment which was done again in Zurich in collaboration with my group at the Institut Quantique. And what you're seeing in this, well, starting to be complicated sample, are in yellow 17 qubits, these star-shaped objects, in which a single logical qubit was encoded. And up to 16 rounds of error corrections were performed. All of the wiggly lines around are the readout resonators and the control lines that you need for this experiment. So there's much work to be done to scale these ideas, but this is really an encouraging start to push these ideas and see how they actually behave in the lab. Okay, so I'm almost done. I see time is flying. Let me just mention one last idea before concluding, and that's the idea that circuit QED is much more than, there's much more to circuit QED than quantum information. Of course, it's a big part, but these ideas of circuit QED have now been used in a host of other subfields. For example, it's now possible to study photonic materials in circuit quantum electrodynamics, or study hybrid quantum systems. So for example, circuit QED with mechanical oscillators or quantum acoustics. But also there's a lot of activities in using and studying the physics of quantum optics at microwave photons. For example, designing better microwave amplifiers, quantum limited amplifiers, and single microwave photodetectors. And something which I find fascinating is that these ideas are now used as a tool for discovery. For example, to accelerate the search for axionic dark matter. There are experiments now using qubits, superconducting qubits, to detect dark matter, to accelerate the search for dark matter. So I'll just flash my conclusion, and I will thank you for your attention.
Thank you, and I hope you will all join me in thanking Alexandre for his wonderful talk and congratulating him on his extremely well-earned medal and on all of his accomplishments.